Welcome to Part 1 in the module on Patterns and Frameworks for Concurrency and Synchronization. In this part of the module, we're going to describe the active object pattern. Let's first start by talking about why we need other patterns for concurrency and synchronization above and beyond what we've talked about so far. If you think about what we've described so far, our main focus has been on patterns and frameworks that make our solutions more modular, more extensible, more reusable, more configurable. But we haven't really worried too much yet about how to make things more high performance, more scalable. We did talk a bit about scalability issues when we discussed the activator pattern. And I talked about how you can use activator to spawn a process per request or a process per connection. That's probably okay for some environments. For a web server, it's a bit overkill to spawn a process per request. There's much better ways to do it, as we'll see here shortly. Likewise, there's also limitations with the purely reactive approaches we focused on for the most part up to now. A reactive approach is nice, it's very simple, but there's a couple of issues you have to be careful of with reactive approaches, having to do with some ways in which they don't work very effectively with certain properties of the TCP/IP protocol, and how they also don't effectively leverage the available parallelism in modern operating systems and hardware. Let's first talk about the protocol issues. TCP has a nice feature built into it called flow control. And the purpose of flow control is to keep a fast sender, like a supercomputer, from overwhelming the buffering and processing resources of a slower receiver, such as a smartphone. Clearly, a supercomputer can generate data a lot faster than a smartphone can consume it, no matter how many cores the smartphone has. So TCP has this model that says, don't send more than a certain amount of data at a time. And if you try to send more data than the receiver can consume, it exerts flow control, which means the sender will block until the flow control abates. Well, there's obviously some problems here. If we're using a reactive approach and flow control occurs on a connection, the server that's reactive will block, waiting for that flow control to abate, and that will starve out any other clients from being able to be processed, which obviously reduces their quality of service. Moreover, you might block because something is temporarily clogged, but you could also block because a malicious client has decided to ignore all the data being sent to it as a way to try to provide some kind of denial of service attack on the server. So we clearly need to have some other approach besides a reactive approach. There's another issue that makes reactive approaches ineffective as well, and that is they don't scale up. If you have hundreds or thousands of users in a big crowd with their smartphones or laptops or other computing devices all pounding away at your server, then you're simply not going to be able to get any kind of response time if there's only one thread of control. So we clearly have to find a way to leverage the available hardware and software much more effectively. To do that, we're going to be talking in this part of the module about applying the active object pattern. And we're going to use this active object pattern to scale up the server performance, by processing the various HTTP requests in separate threads of control. In particular, we're going to have a separate thread of control for each connection that comes in from a client. In general, the active object pattern defines the units of concurrency to be service requests that are run on a component. And it arranges to have these requests for service work in a manner where the method that requests the service is decoupled from the method that executes the service. So those can run concurrently. We're going to talk about a number of different ways in which this pattern can be implemented, and we're going to start by talking about the structural dimensions at first. It's also important to realize as we do this discussion that there's many pieces to the complete active object pattern, not all of which are used in practice all the time. And so I'll make sure to talk about those issues as we go through this example. But first, let's talk about the structure. One part of the structure involves the client that runs in a thread of control and invokes a method on the active object. And this method, as we'll see in a second, is actually invoked on a proxy. And what happens is that that proxy converts that method call into a message called a method request. And that method request is passed over to the active object, where it's enqueued in some kind of activation list that the active object's scheduler manages. And then at some later point in time, that scheduler, running in a separate thread of control from the client, will dequeue the message and do something with it. If you take a look at this URL at the bottom of the slide, you'll see a paper that goes into more details about the active object pattern. This pattern also is described in the POSA 2 book in great detail. Here's a dynamic view that gives you a little bit more perspective on what's happening as these various interactions take place between the various roles in the pattern. We start out by having a client invoke a method call on a proxy. And of course, we use the proxy pattern. That's a gang of 4 pattern, as well as a POSA 1 pattern, to be able to decouple the way in which you invoke an operation from where the operation actually runs. In our particular case, the proxy will convert the method request, the method call, into a message called a method request. And this method request basically contains message fields that correspond to the data. It keeps track of the name of the method. It may also have some return information as well. And it gets bundled up into an object that you can use to pass from the proxy back into the active object portion. The proxy part also creates something called a future. And the future is going to be used to pass back to the client later so it can subsequently retrieve the results, if any, that occur when the active object invokes this request. What happens next is that the method request is then passed to the scheduler, and the scheduler then enqueues this method request on an activation list, and it gives back the future to the client. And then at some point down the road, and this depends on a variety of different factors. It depends on scheduling constraints that the scheduler may know about. It may depend on certain guard conditions that the method request knows about. It may simply run things in FIFO order. It all depends on how you implement things. The scheduler will enqueue the request and then later pull it off, convert it back into a method call onto the servant that actually carries out the request. And after the servant is done, the servant will end up, as a side effect, updating the future so the client can then get the result. There's a couple of ways in which clients can get results from futures. One way they can do it is they can periodically poll the future and say, is the result ready? Is the result ready? Is the result ready? Or they might do a timed poll. They'll say, I'll wait up to a couple seconds for the result, and then I'll go off and do some other things. That's one model. An alternative model, which probably is more scalable in many ways, is to use callbacks. So what happens here is when the future's value is updated, when the servant has finished its processing, then a callback takes place to deliver those results back to the client. So let's talk about how we can apply the active object pattern to our JAWS web server. One way to do this, which is supported quite nicely in ACE, is to implement active objects by making a very small number of tweaks to our existing acceptor connector-based version, which itself, as you recall, is based on the ACE reactor and just extends that in certain ways. So what we're going to do here is we're going to create some new capabilities that inherit from ACE acceptor and ACE service handler, and they're going to create new classes that run things as an active object as opposed to a reactive approach. In particular, we create a new subclass of service handler called TPC, for thread per connection, HTTP handler. And that's going to run as an active object, and it's going to receive the request data that comes in from a client on a per connection basis and process that data and then send it back. The nice particular way of doing things is it allows us to be able to have different threads for different connections. So we have a thread per connection model. And if those connections happen to block, or if those threads happen to block while they're processing the data on the connection due to flow control or some other condition, not a problem. Other threads handling other requests from other connections can proceed concurrently. Notice that this particular way of doing things has a couple of interesting variations that are above and beyond what you might expect if you just look at the active object pattern description in a simple way. One thing to note here is that part of the processing that's taking place here is actually occurring inside the operating system kernel. So getting the data that comes in from the network sockets and then converting it into something that can be passed as a method request up to the user space thread, that's done initially from the kernel side. The actual active object portion is running in the TPC HTTP handler in a separate thread of control. And so that's going to be able to run separately, but that's passing the data between the different layers through this socket connection. Another thing to note here is that we're only doing a subset of the full-blown active object pattern. We're not really handling futures. We're not really doing servants. We're doing more of the message passing variant of this pattern. And if you read the POSA 2 book or the other URL I sent you and showed you before, that will give you an idea of how these different variants work. It's actually very common to use the variants for a number of reasons we'll talk about. So let's talk about some of the benefits and limitations of this pattern. Some of the benefits are you can actually use concurrency and simplify synchronization complexity by treating method requests as the unit of concurrent execution. So this is a fairly intuitive thing for an object-oriented developer to make a method call on an object, and the fact that those methods turn into these messages or method requests and are run concurrently, that's kind of icing on the cake to be able to get things to run better. You can also have a scheduler that can use various kinds of sophisticated constraint-based reasoning and guards and so on in order to determine the order in which to run these requests. We're not really doing that in our particular example here. We're doing things in a more FIFO order, but the complete pattern can be used more flexibly. Another benefit of this pattern, of course, is that if your operating system and hardware support it, you can transparently leverage the parallelism that's available. So you can have these different method requests running in separate threads of control. Another benefit that you might be able to get from this pattern is that there are times in which the method that invokes the operation and the order in which things are invoked will be different from the order in which the methods are actually executed by the scheduler. You might order things in a way that satisfies scheduling constraints. You might order things in a way that satisfies various priorities, so higher priority users get preference over lower priority users, and so on and so forth. So those are some of the benefits of the pattern. As always, there are some limitations. One of the limitations that you often run into with these kinds of concurrency models is that there is some overhead incurred with respect to context switching, synchronization, data movement, memory allocation, deallocation, copying, and so on, needed to move things between these different boundaries, between the different thread boundaries. And if you're running long-running operations, not really an issue. If you're running short-running operations, the overhead may actually swamp the performance benefits if you're not careful. Another potential issue here is that when you start having multiple threads of control running, then your debugging can be more complicated. It may take a while to figure out how to set breakpoints. Some environments don't do a very good job of supporting concurrent debugging, and even environments that have pretty good support for concurrent debugging, you may experience the condition where the behavior you get when you're in the debugger might not match the behavior you get when you're running in the production environment, because the scheduling order may be different, things may be serialized and synchronized in different ways. So certain types of defects and faults may be hard to identify. The last thing I want to reemphasize here is that in practice, people often use subsets of active object more than they will implement the full-blown pattern. And there's nothing wrong with that. It's a very useful way to think about structuring your software. And even if you don't need to have the complete proxy experience, the complete servant experience, even in situations where you don't need complicated schedulers with complicated constraints and so on, you can still get a benefit from a design point of view of thinking about your program in terms of active objects.